So now it is my great pleasure to introduce a good friend and colleague of mine, Christian Riedel from Technical University of Munich. And in this first of the two talks of this session, we will hear about how to observe spin wave foldover in plain YIG films. So with that, Christian.
Thank you for this kind introduction. So yeah, hello, and thank you for letting me being here. And it's a pleasure to give a talk here. As Florian already mentioned, I will give you an idea today about how we observe spin waves in our labs and how we get some nonlinear behavior of spin waves in the forward volume regime. But first, let me tell you why we should use spin waves. So there's a big research field called magnonics, which is using the magnon, which is the quasi-particle of our spin waves. So magnonics is a promising field for having information processing with magnons. And as you can see here in the rather complex sketch from a paper from Ji Wang from last year, it demonstrates that the magnons or magnonics can be a different approach to conventional technology, because the main difference and the main advantage is that you don't need charge current to transport information or to process the data, but pure spins to process the information. And this gives you the advantage that you don't have any heat losses, which always comes if you have electrical charge flowing. So it was demonstrated in quite some examples. For example, here in spin wave optics, which demonstrates you how you can manipulate the propagation direction of spin waves by changing the properties of your material, which we will also touch today. Also, just for example, you can create some spin wave beams to just attract some channels, one or two in this case, which is called spin wave caustics or caustic-like beams. There's also some rather new field which is called inverse design, where they simulate the design before they fabricate it actually, and then they can guarantee that you get spin wave propagation characteristics which you actually want to have. Also some very, let's say, advanced theories or models are that there are concepts that you use spin waves even for neural networks. There are concepts to use spin waves for different computing concepts. But however, magnonics is still predominantly in academic research and didn't find the way to industry yet. So anyway, through my talk, I already told you why we should or can have a look to spin waves. I will now tell you what spin waves are, because if you don't know what they are, then it might be a bit challenging to understand. The first slide, how to observe the spin waves in our lab, at least one way, they are several ways. Then also we will touch the properties, the propagation properties of spin waves, which can be anisotropic or isotropic. And in the last part, I will actually cover the title of this talk. I will show you the nonlinear behavior of spin waves and how you can achieve a foldover process for spin waves. Okay, let's start. What are spin waves actually? Well, as the name already suggests, you need a spin or a dipolar moment, and for this you need a magnetic material with a long-range order, namely a ferromagnet or a ferrimagnetic material. So if you apply an external magnetic field to your material, which is indicated by this red arrow here, you can actually align all the magnetic moments or the spins in the same direction than the external magnetic field, as long as it's sufficiently high to align it in the same direction. So what we want now, we want to excite a wave inside our materials. We want to propagate some information from A to B, and for this we have to excite our magnetization to precess. So we have to excite it outside of the equilibrium stage, and with this we can put an excitation source on top of our magnetic material, which is in the easiest case an antenna, where we send a radio frequency current through it. And while sending the radio frequency current through it, we create an Ørsted field around this conductor, and this Ørsted field actually gives you a torque on the magnetization. And with this, if you do so, you can actually excite the spins to precess, and due to the next neighbor interaction, you will form a wave where we can actually define a k-vector and a wavelength as for also other ways. In the case I show you here, when the magnetization is pointed out of the sample plane, we call this forward volume spin waves, and the specialty on this dispersion on this spin wave mode is that the dispersion relation is actually isotropic. As you can see here on the bottom left image, is that if we have for a given external magnetic field, you have the characteristic of the k vector in x and y direction, and you can see here that you have a spherical distribution of this, which meaning that it doesn't matter for your spin wave in which direction it propagates. It always have the isotropic dispersion. But we can also align the magnetization within our sample plane, and if we align the magnetization in a way that it's perpendicular to our k vector, then we name this Demon-Eschbach spin waves. On the other hand, we can also align the magnetization perpendicular to our excitation source, and if we choose this geometry, the k vector actually and also the phase velocity is negative, and it seems that the wave propagates backwards, and that's why we named this spin waves backward volume modes. So the two modes I showed you before, with the in-plane magnetization, they are actually anisotropic behavior, meaning that if you are looking at the dispersion relation for a given external magnetic field, for this spin wave, it strongly depends on if they propagate in the x direction or in the y direction with respect to the external magnetic field and the k vector. So mathematically, we can describe the spin waves by the dispersion relation, which contains quite some material parameters and also some shape parameters. But what we are usually interested in is the how our k vector or our wavelength of our spin wave develops if we're changing the frequency, the excitation frequency. And you can see this here again, if you plot all the dispersion relation for all three spin wave modes, or isometric spin wave modes, then you can see how they behave. And here for the backward volume mode, as you can see here, you can see that there's a negative slope at the beginning, which is giving you the group velocity, and this is why, as we have seen before, the phase propagates backwards. So how do we observe the spin waves? We observe the spin waves by so-called time-resolved magneto-optical Kerr microscopy, or short TMOG. Usually we are using a ferrimagnet called yttrium iron garnet, which is the standard material in magnonics, because it has a very low damping, so meaning that your spin waves can propagate in the millimeter range. It gives you a nice Kerr contrast, so it's just easy to handle, let's say. So in our case, we had a 200 nanometer thick YIG layer on top of GGG. And to excite the spin waves, as I showed before, we are using a coplanar waveguide, which is our excitation source, and this is made out of 100 nanometer gold in this case. So as I said before, we are sending an RF current through our antenna, creating this oscillating Ørsted field, and with this we can now excite the spin waves. And you can see here in the grayscale, which indicates the Z component of the magnetization, that we actually excite kind of a plane wave propagating away from the coplanar waveguide, hitting to a diffraction, creating interesting pattern, which we will touch later again. So these spin waves and the magnetization oscillates in the gigahertz regime, which means that if you want to measure them and if you want to have pictures like this, we need a process which is faster than the gigahertz regime. And with this, we are using femtosecond laser pulses. Important is that we synchronize the repetition rate of our femtosecond laser pulses, in this case 80 megahertz, with the phase of our RF generation, because this is a so-called stroboscopic measurement principle. So we always want to hit our magnetization position with the femtosecond laser pulse always at the very same phase if you don't move in space. However, we send the femtosecond laser pulses to a beam splitter, and we focus on, we guide a small fraction of the femtosecond laser intensity to an objective lens. We diffraction limited focus this on the sample surface, and while reflecting at the magnetic surface, linearly polarized light, indicated by this black arrow here, undergoes a so-called Kerr rotation, which means that the polarization direction rotates, which is directly proportional to the magnetization of your sample. This is actually indicated by this black sphere here, meaning that we are not perfectly linearly polarized anymore, but the polarization is a little bit rotated. We then collect the same back of the light by the same objective lens, and now guiding it through the beam splitter to an optical beam path, which contains an optic Wollaston prism, which splits our two polarization components to the orthogonal components, meaning that if we change the polarization direction, we would also change the ratio of the light being in this path and being in this path. And now we are using a balanced photodetector. This is for common mode rejection, for example, and we are building the differential signal from this, using a lock-in to enhance the signal-to-noise ratio a little bit. Of course, we need a computer to kind of observe the signal. So I already said that it's a stroboscopic measurements principle. The spatial resolution which we can achieve depends on the wavelength we are using, but it's usually down to 300 nanometers. Everything is, let's say, well aligned and works quite well. Whereas the temporal resolution depends on our femtosecond laser pulse length, which can go up to terahertz. So the femtosecond laser pulses are usually in the order of 100 femtoseconds, 200 femtoseconds, whereas you can reach terahertz easily, which we may not touch today. So now it's coming to the anisotropic spin wave behavior and the dispersion. As I told you before, we are always interested in the properties of the spin waves, can be described by the dispersion relation. And what we usually do is we excite our spin waves in our plane film, then we scan with our laser or with our TMOG setup away from the coplanar waveguide, from the excitation source, and we measure the propagated spin wave, the wavelengths in space, as a function of the external magnetic field, meaning that we make a line scan in x direction in this case, we change the external magnetic field, we make the very same line scan again, and with this we can observe that the spin wavelengths, as you can see here, changes with respect to the external magnetic field. Here for the Demann-Eschbach case, you can see that we actually increase the spin wave if we the wavelengths if we increase the external magnetic field, whereas if we have the backward volume geometry, you can see here that if we increase the external magnetic field, we actually decrease the wavelengths. An interesting part which we discovered here by measuring the dispersion relation is an area where it seemed that the spin wave propagation is strongly suppressed. So we had a deeper look in this, and then we were thinking about, okay, there might be not only propagating plane waves within the film area, but there might also be so-called perpendicular standing spin waves, which are spin waves located along the thickness, in this case our 200 nanometer YIG, and which are standing waves there, which can have either zero mode, so there's no amplitude, it's kind of a homogeneous oscillating mode, and there can also higher modes with nodes within this distributed along the thickness of this film. And if you check the dispersion relation again for Demann-Eschbach and for backward volume, you can actually see, now considering the PSSW modes, we can see that for backward volume modes, there's no interaction between these different modes at all. But if you check the Demann-Eschbach modes, we can see that there is a crossing of the n equals 0 and n equals 1 mode. And if you have a deeper look into the area here where we saw the suppressed propagation of the spin waves, we extract the K value from this, and we, by using TetraX, which is a Python package for magnetic simulations, we can actually see that there is indeed an anti-crossing of these two modes, meaning that if you have an anti-crossing, they are strongly coupled to each other. And with this, as the slope of our dispersion here is equal to the group velocity, it becomes almost zero here, meaning that when the group velocity becomes almost zero, there's no propagation of a wave anymore. So if you want to now investigate the whole in-plane dispersion relation for backward volume and for Demann-Eschbach at the very same time, we should excite all the k vectors possible. With this, you ideally would like to use a point-like spin wave source, and for this, and also for other reasons, we made a sample with diffraction grading inside, meaning that we had our 200 nanometer YIG film. We etched just holes inside through the whole 200 nanometer YIG film. We then excited our spin waves again in the Demann-Eschbach geometry from the coplanar waveguide, and we made two-dimensional measurements in x and y for this area here. And if you can see here, we excite a plane spin wave propagating away from the coplanar waveguide, hitting our diffraction grading, and now we can see quite some things happen here. So first of all, you can see that we have a diffraction pattern, which is a beam-like type behind the diffraction grading. What you can also see is, especially for the 42 and 44 millitesla measurements, is that the initial wavelength amplitude is also transmitted to the long-range order interactions. So we don't only see this emission of the spin wave beams, let's say, but you can also see the initial amplitude or initial wavelength gets transmitted. And furthermore, especially for the 44 millitesla, you can see that the beam pattern or the diffraction pattern is not only on the right-hand side of the diffraction grading, but is also observable on the left-hand side of the diffraction grading. And this brought us to the point that actually every dot or every antidot acts in this case as a point-like spin wave source, meaning that from this you excite every k vector possible, and if you now extract the k values, the two-dimensional k values for the, what do we have, for the 40 millitesla and the 44 millitesla, for example, you can actually see that you have the kx and ky distribution, which is similar to what we have seen before in the theoretical approach. So it's just a cutout of this inner part here. Furthermore, if you jig a little bit closer on this isofrequency line here, you can see that there's a kind of a turnaround, not kind of, but there is a turnaround point in the dispersion relation, meaning that the second derivative of the dkx over dky is becomes 0. At this point, this is called a so-called caustic point, which meaning that many k vectors have the same direction of the group velocity, and if you have thus, also in optics, you are forming a so-called caustic beam. And this is actually why we have these spin wave beams, because we are hitting almost a caustic point and emitting spin wave beams with this. So now coming to the isotropic dispersion relation, where we actually align the external magnetic field out of the plane. If we use the same sample, having our diffraction grating inside, we're exciting spin waves on the left-hand side, you can actually see that we are emitting nicely round or spherical shaped spin waves. It's an indicator also, if you check this isofrequency line here, that it doesn't matter for the spin wave anymore if it propagates in x or y direction. So we did some further experiments. So we actually changed this time the frequency by a given external magnetic field, and we investigated the interference pattern behind the diffraction grating for forward volume modes. And if you do the 2D FFT from the areas indicated by this rectangles there, you can see that you have a spherical-like k-vector distribution, which also shows you that we have a point-like excitation. Initially, we wanted to investigate a so-called Talbot effect, which is an effect from optics, meaning that you have a self-imaging of a diffraction grating, which you can kind of see here. So here you have the diffraction grating, and here, and here, and here, and here we have, or we thought we have the image of our excitation source. To know or to compare this with the theory, you actually need the wavelength of your incident wave, with your incident wave coming from your antenna. With this, we wanted to do the very same as before, so we just scan a wave from the coplanar waveguide, changing the external magnetic field, and we wanted to extract the wavelengths. We did this on the opposite side than the diffraction grating, otherwise you will be disturbed by the diffraction grating effect. And what we found is that if we check the spin wave amplitude here, if we scan away from the coplanar waveguide in y direction as a function of the external magnetic field, in this case, as it's important soon, we reduced the external magnetic field from higher values to lower values. We found a few interesting things. So first, you can see that the propagation length strongly depends on the external magnetic field and also on the k vector or on the wavelength, as you can see here in the phase plot of the spin wave. Then we thought, okay, let's check if it fits to the dispersion relation. So we extracted the k values again from our measurement. We compared this with the dispersion relation, and we actually found it doesn't fit at all. So we were wondering, but then we also thought, okay, also our experiments, they were sometimes hard to reproduce. So we actually swapped the magnetic field from up to down. So this time we did the very same measurement, just we clicked start again with other values in our setup. We swept the magnetic field from down to up, and we have seen that there's a totally different behavior for the spin wave excitation. So you actually have a certain jump in the amplitude and in the excitation of your spin wave suddenly. If you look very close, and if you believe it somehow, on the area on the left-hand side of this high amplitude excitation, you can see that there might still be some propagating spin waves, but with a much lower amplitude. So we extracted the k value from there as well, and we saw, even though it was very noisy, it somehow fit more to the dispersion relation, let's say. So we wanted to also have a deeper look into this. And after some literature research, we found that Xi Wang in 2003 observed something similar already with Prion light scattering, another optical technique, to observe something like this. And they actually came up with the idea that this is a nonlinear oscillator behavior. So now we also wanted to check what the nonlinear oscillator, if it fits to the nonlinear behavior. So first, the linear oscillator behavior is very simple. If you have a resonance frequency here, then your amplitude of your whatever oscillator, string oscillator in the easiest case, does not depend on if you scan from low to higher values through your resonance or the other way around. It always stays at the very same frequency and at the very same amplitude. However, if you're in the nonlinear regime, it does depend strongly on the direction which you're sweeping your excitation field. In this case, to make it more comparable to our experiments, we use the magnetic field here, whereas 0 is the magnetic field on which we would hit the resonance. And now there are two different cases. One is that you can have a so-called softening or a so-called hardening of your resonance, meaning that you either shift the resonance to higher values or to lower values. We now will focus on the softening, meaning that the resonance shifts to lower field values. And if you actually follow what would happen, so if you would sweep the external magnetic field up, we would expect a sudden jump in amplitude, and after the sudden jump we would expect a decreasing in the amplitude again, while as if we sweep it back, we would expect that we will not jump down, but we will continue increasing with the amplitude until we drop down there again. So if you now check the measurements which I have shown you before, if you check the upsweep, we sweep the external magnetic field up, then there's a sudden jump in amplitude, which we can also see here, sudden jump in amplitude, and then we have a reduce in the amplitude again. And if you check the color scale here, and you follow this line on the bottom here, you can also see that we see something very similar there. On the other hand, if we go now backwards, and if we sweep the magnetic field from up to down, we should not jump back, but we should continually increasing the amplitude before we jumping down again. And this you can also see here. You can see that the contrast which from the spin wave amplitude increases up to a level which we cannot explain right now, but then it drops suddenly to almost 0. So this was always at the opposite side of this diffraction grating, and we were not sure if this is somehow affecting our measurements. So we went to a YIG film with no structure on it, just a plain YIG film to be sure that we are not disturbed by anything. So we did the very same measurement. So we sweep the external magnetic field at a given RF frequency at a single point next to our coplanar waveguide, just to see when we hit our resonance area. We did this for different frequencies to be sure that there's not an experimental artifact and that this is independent of the excitation frequency. And as you can see here for the upsweep, you can see that the resonance area is comparably small to the resonance area for the downsweeps, meaning that this nonlinear oscillator behavior is, at least for a certain frequency range, not dependent on the frequency. If you now check a certain frequency, 6 gigahertz in this case, and we just plot the upsweep here and the downsweep again over each other, you can actually see that the excitation behavior is very similar for both up and down sweep, but not for this Foldover window, which is the nonlinear, explained by the nonlinear behavior. And here we have actually a Foldover window from about 10 millitesla, which is quite something. However, we also wanted to have a deeper look into the spin wave propagation behavior for this window. So we again scanned our laser across the coplanar waveguide on both sides of the sample. As you can see here, the Y scan 0 is where the coplanar waveguide is here. And we did the same. We swept the external magnetic field from lower values to higher values. And we saw the same behavior, but we have seen some other special things. For example, you can see here within the coplanar waveguide, you can see that there's a strong excitation of the, let's say, magnetization to process. I wouldn't call it a spin wave here, but you see that it hardly propagates away from the coplanar waveguide. Also, if you check the phase image and if you put a little bit more effort in a good signal to noise ratio, and then you can also see for the lower spin wave amplitude area that there is indeed a propagating spin wave observable. And if you now extract the K values from this area and also from the other area, which is quite messy, but here you can see that it fits quite well to the dispersion relation. Why I plotted also another dispersion, just theoretically I put this in. This is the dispersion relation for the forward volume spin wave with the first perpendicular standing spin wave mode, which I have shown you before for the in-plane magnetization. And this is actually quite reasonable that we may have a crossing here in this area, that we excite magnetization to process at the source, but it cannot propagate away from the excitation source. So with this, I would like to sum up. So I hope I gave you an idea how we do measure spin waves in our lab by TR-MOOC. I showed you the properties of spin waves, which can be either isotropic or anisotropic in yttrium iron garnet, that's standard magnetics material. I've shown you that the spin wave or different spin wave modes can actually hybridize with each other and forming some anti-crossing because they are strongly coupled. We have shown you a Foldover behavior for the nonlinear behavior for the spin waves, and also that we can indeed excite propagating spin waves fitting to the dispersion relation, but also an area which is quite chaotic, which we have to look further into this. So this TR-MOOC and the technique we are using is a platform also to investigate magnons also at low temperatures, even though I haven't shown you here the low temperature behavior, but we are also doing this in our labs. Thank you.
Okay, thank you, Christian, for this very nice insights into magnonics and the overview. Oh, there's already a couple of questions.
Thank you very much. I have two questions. The first one is the wavelengths of your spin wave. It's on order of a few micrometers, or
yes.
Okay. And what determines that? The separation. I mean, your source, or is it something else that?
It's mainly the source. Yeah. So if you put the coplanar waveguide, so if you do a FFT from your coplanar waveguide or from your antenna, a spatial FFT, then that gives you the excitation spectrum which you can actually excite. So you can excite shorter wavelengths, but this is inefficient with such a big, let's say, more or less macroscopic coplanar waveguide. And furthermore, we could not be able to measure them. So we are limited to 300 nanometers of our wavelengths.
Yeah.
Everything below this we have to go to
I was wondering in this case then, if you instead of using this source with the same width, if you use like a wedge, would you be able to generate like any kind of wavelengths with that source?
Theoretically, yes. Practically, I think the impedance match would be very horrible, which meaning that maybe as thinner you get, you get the power equally distributed. I think the problem is that you don't get much RF power then through it anymore. But if you use an amplifier and so on and so forth, then yes, people are actually doing this. If they do short or spin waves in the exchange regime, where the wavelength gets shorter and shorter, then they are doing also smaller antennas, but then you have to go to scanning transmission X-ray microscopy, for example, to get a higher spatial resolution.
I see. And the second question is, can you prepare like stripes of out-of-plane magnetized and then another stripe with in-plane magnetized and see what happens at the interface, whether there will be some conversion of the waves or reflection? And and also like a follow-up is, can you actually make some resonators for the spin waves?
Yeah, this has been shown,
like this?
not for out-of-plane and in-plane at the same time. Maybe I guess it's a bit tricky. So because you may have to use different materials for this. But what people actually did is they used YIG, what else? And then they put another ferromagnet on top of it, permalloy, or cobalt iron boron it was, I think so. 2 stripes from it. And with this they actually fabricated a fabric pyro interferometer with this, because you're changing the dispersion relation inside your material where your spin wave propagates, and with this you always get reflections and transmission ratio.
So it will not be, this border will not be sharp, it will be some kind of adiabatic.
It depends on how you change the dispersion. So if you have it, so for example, what we have shown is we have used this area here, for example, to make a hard stop for our propagating spin waves at a certain position. Because if you use an in-plane magnetic field, for example, and you have a wedge, for example, as you just suggested, then you have at the border of the edge, you have a reduced magnetic field because of surface charges, and that actually can allow you to shift the dispersion to this area just by the shape anisotropy. And this we already showed, and there you get your abrupt stop. Yes.
Thanks.
You're welcome. Thank you.
Okay. Thanks for the nice talk. I wanted to ask about the nonlinear oscillator behavior that you showed. On the one hand, kind of, do you know what's the physical origin of the nonlinearity? And on the other hand, kind of, like in modeling, what type of non-linearity is it? If I think of a harmonic oscillator, what term do I need to add to get this?
So why we see this only in out-of-plane geometry but not in in-plane, for example, is that the oscillation amplitude of our spin waves can be much higher for the out-of-plane magnetization, because you can align, if your magnetization precesses, then it's not limited by any surfaces to process, but it can process in the film very easily. This is why we reach these high amplitudes, and this is why we're coming to the nonlinear behavior. We tried to model this with a Duffing oscillator, but it's not quite the same energy landscape, so we have to call it Duffing-like or whatever. That's why I never mentioned Duffing, but just nonlinear oscillator.
Christian, my question goes basically into exactly this direction. So you nicely introduced to us the Duffing oscillator, and if I'm looking at the diagram on the top right, then it is not really looking, or it looks more complex. So can you give us a little bit of a hint what's going on there, and what kind of magnons are involved there?
Okay, so I guess the question, if I understand it correctly, there's not only a foldover, but also a lot of other things going on. Okay, so yes, that's true. And this is actually, we have seen this for other frequencies as well. Here we did the very same for different frequencies, and we have seen some different behavior for this spin waves. Starting from here, which is 10 gigahertz, don't be confused with this 1 megahertz, it's a measurement technique issue. The foldover process is kind of gone, but we assume that this is because the excitation efficiency, because our CPWs are not nicely impedance matched, cannot excite the high amplitude anymore, and with this you don't get this nonlinear process anymore. But however, for the others, you see that there's also some dips going on here, or here it's even more prominent. So I have to do the calculation or the simulation, yes, but we have the idea that this can come from the hybridization of the forward volume with PSSW mode, because this suppresses you the propagation of your spin wave. And all the rest, then you also have to fold this is the spin wave amplitude, right? You have to fold the signal with the excitation efficiency of your coplanar waveguide in the K-space. And so I think it's, as you said, it's rather complex. Welcome.
So with that, I think we can thank Christian again, of course, and move on to our next speaker.